that I've done this class, but it's new and improved. It's got great stuff. We're gonna take a look at all the good parts of it and hopefully make this math not as scary as it might seem. So without further ado, let's jump right in. I loved this here. I added this numbers and variables and symbols. Oh my, reference to The Wizard of Oz. And if you haven't seen the prequel Wicked, it's amazing, amazing. But let's jump in and talk a little bit about the details. Now I'm going to mute my video. That way we don't get any lag and we'll get a really good stream as we're looking through it. So a few things about our week 1 to-do list. We've got 2 discussions. I hope you have taken a moment to read the prompts. There's some great opportunities for discussion here. I am super excited to be jumping into these discussions this week. Please do not get overwhelmed by thinking, oh, this is a math class and how are we going to do discussions in math class? Read the prompt and start with something. I view learning as a journey. Okay, I do not view it as a snapshot. Well, what do you mean by that, Dr. May? Well, let me explain. I view learning as we start where we're at and we get better. Okay, so if the first time you post something to the discussion board and it's not 100% correct, that's okay. You're going to have the opportunity to fix it. Because remember, I view learning as a journey, not as a snapshot. So the idea is that we have to start from where we're at. We can't start from anywhere else. Start from where we're at, and then we get better. And that's all we're aiming for as we are learning through this course. So with that in mind, with our discussions, start somewhere, right? And I know our lab instructor is going to be hosting some sessions that walk through, actually putting pencil to the paper, typing it out and putting it and getting your reference and all of that good stuff for your discussions. But I would encourage you to start somewhere and then view it as the journey that it is. We've got an assignment now, which the assignment, we have a fabulous template. In that template, I have put video examples for you to walk you through completing each of the 5 problems there. Please don't wait till the last minute on the assignment. You want to have a head start with that so that you don't get bogged down by the last minute, okay? The assessment, good questions to answer for this week. Then the live lecture quiz, of course, we'll be going over things that will help you with the answering those correctly. And then, of course, the daily checkpoints. Remember that 4 of the daily checkpoints are required and 3 of them are extra credit. So take advantage of those. All right, so let's take a look at the objectives for week 1. Now we have quite a few of them that we need to be mindful of. What I'm going to do through our session today is I'm going to show you the learning objective, then I'm going to kind of explain it, and then I'm going to give you 2 to 3 different ways we can ask that question. 2 to 3 different ways you might see that learning objective asked on an assessment, on an assignment, and so forth. Okay, so like I said, we have 5 of them, and so I want to be mindful of your time. Now, before I jump into the learning objectives, I want to make mention that our session right now will be around 45 minutes long. The session I hold again tomorrow will be the same content, different examples, okay? So that means in this 45-minute session, you can get everything you need to answer the live lecture quiz, to understand the assessment, to do well on the assignment. All of the content is here in this session. If, however, you're still unsure about a particular concept or you want to see more examples, that would be the second session in the week, okay? So I'm going to have fresh and new examples on the second session, but the content and the learning objectives will be the same. So that's how I'll split it up for you. let's jump into that first one. The very first learning objective is to explain what a numerical set is and identify types of numerical sets. This is just a lot of vocabulary, okay? So hang with me so you can understand the vocabulary. I'm going to try to put it in context for you so you can see where we're coming from with each of these. Now, a set is a collection of items. So when we teach children numbers, we begin with what are called the natural numbers, okay? So when you teach a child how to count, you teach them 1, 2, 3, right? Like I'm notorious for I had a little boy here, my cousin's son was here on Saturday, and I said, Camden, can you count for me? And he started 1, 2, right? Like that's how we teach children to count. Those counting numbers are what we call natural numbers. Counting numbers are natural numbers. They are the first thing we teach children. So at the bottom here, you do see the examples of those. Now, once a child has a grasp of the counting numbers, then we teach them, you don't have any, you have no more candy, right? You have no more pencils, you have no more toys. And then, so we add the number 0. So when you add the number 0, you have the whole numbers, okay? A lot of people think of the whole having an O in it, a 0, and therefore that being whole numbers. So after natural numbers, then we add the concept of not having any toys or any more candy, and those are the whole numbers. Now, next in school then, your children probably learned fractions, right? Somewhere around 3rd grade, we introduced the idea of here's a picture, what fraction represents the shaded sections, and those fraction numbers are the rational numbers. The rational numbers are those that can be written as a fraction. Notice the symbol, though, for the rational numbers is not an R, it's a Q. You'll see why it's not an R here in just a minute, but for now it is a Q, and all of the rational numbers are those that can be written as fractions. Now you may be looking at those examples at the bottom and saying, uh-oh, wait a minute, square root of 16, why is that in the rational numbers? That's because the square root of 16 is 4, which it can be written as a fraction, therefore square root of 16 is included in the rational numbers. You maybe say, oh, what about that 0.5? Well, it can be written as a fraction, as 1/2. So it too is included in the rational numbers. So it's not that it is written as a fraction, it's that it can be written as a fraction. So remember, we teach the children to count natural numbers. Then we add the concept of a 0. That gives us the whole numbers. Then we start them in on fractions. And somewhere around 5th, 6th, or 7th grade, we introduce the concept of having negative numbers, and those are the integers. Probably you or your children started with a number line, and you had these numbers that were to the left of 0. Those were the negative numbers. And notice that I will say they are nice negative numbers. And what do I mean by that? Well, there's not any fractions. There's not any decimals. They're just the counting numbers or the whole numbers and the negatives, okay? And the integers get this symbol of Z. Okay, so realize we actually teach these to children. We actually expose them to these type of numbers, whether we call them by their names or not. Maybe not. Okay, my 3rd grader can write a fraction, but he has no idea that that's a rational number. Okay, we don't put a label on it because the child doesn't need to have the label at that point in time. However, you and I have been dealing with fractions for a long time, so now we can see the benefit of knowing the label. That's really all of these sets are. There's just labels for groups of numbers. Okay, I like this chart. I'm hoping it's going to help you as you're maneuvering through some of the concepts for this week. Let's look, we have 4 more sets of numbers. Now the first 2 on the left are probably going to be encountered by a child in an intro algebra class, okay? Could be Algebra 1 in high school, could be in a beginning algebra class. So the first group are called irrationals. Now the rationals, remember, those were the ones that could be written as fractions. So the irrationals are those that cannot be written as fractions. And so look at some of our examples here. We've got pi. Hope you were able to celebrate Pi Day yesterday. So yesterday, March 14th, 3/14 was Pi Day. And that's where we celebrate the contributions of pi. If you want to see, so I posted some things on my social media yesterday on my Instagram about some things we know about pi. And I'll be happy to share those if you want to check those out. And so these irrational numbers like pi cannot be written as a fraction. And so that's why we call them irrationals. Now, the second set are the real numbers. So these are any number, the real numbers include any number that can be written on a number line. So that's going to be your fractions, your rational numbers. It's going to be your integers, your positives and negatives. It's going to be your irrationals. Like I can put pi on a number line, even though it can't be written as a fraction. So a real number is anything that can be put on a number line. Now the last 2 are probably the 2 that may be the most foreign to you. And they are encountered in probably a second year algebra class, a little bit more advanced class, maybe an Algebra 2, sometimes it's introduced, sometimes it's not. And that's when we introduce the imaginary numbers. So these are numbers that include I. I is a symbol we use to represent the square root of -1. And any number that has an I with it is considered an imaginary number. And the final group are the complex numbers. These are the imaginary numbers plus or minus a real number. So this is where it might, oops, sorry about that. This might look something like 2 plus 3i. Okay, so it has a real number, that's the 2, and it has an imaginary number, the 3i, complex numbers. Now, our course is going to focus mainly on the first 4. We'll deal a little bit with the irrationals and reals, and we'll just mention the imaginaries and complex, okay? So if you're going, ooh, imaginary numbers, no, thank you. No worries, you're gonna be okay. We're not gonna spend a ton of time on those. But again, I love the chart. I think it's very beneficial. I think it's something I definitely wanna have in my notes so that I can reference back when I'm doing my assessment or when I'm looking at my assignment. Okay. So how would those types of questions be asked? Okay, what kind of questions am I going to see that are about the number systems? Well, I'm glad you asked. Here's the first example. Which set is an example of an integer number system? So remember from our chart that integers are whole numbers with no fractions. They include positives, negatives, and zeros. Okay, so which of our groups here, A, B, C, D, include whole numbers that have no fractions and positives, negatives, and zeros? Exactly, A. That's what we get. Yeah, so this is one way you can be asked to identify which number set. Here's another type of question you might see. Which statement is true regarding irrational number sets? Numbers that can be written as fractions, numbers that can be written as, numbers that cannot be written as fractions, numbers that fall anywhere on the number line, or numbers that can be real or imaginary. So again, we go back to our irrational part of the chart. It tells us that irrational numbers are, this is the type of set that includes numbers that are not rational. Rationals can be written as fractions. Irrational numbers cannot. So which of these is true? Yes, thank you, Rocky. Thank you, Kellen. B, now, irrationals are numbers that cannot be written as fractions. But you see the type of questions, right? You see the type. We're classifying. We're looking at sets and we're saying, yes, it can be integers. Yes, it can be rational. Or we're making statements about the group together that we know to be true. Okay, so let's move to the next learning objective. And that is to summarize an exponent's effect on a number. When we see numbers, expressions like this that have 4 to the 5th power, I have many students who just do 4 times 5. And it breaks my heart because 4 to the 5th power is so much more than that. It really means that we would write the 4 5 times. We would write the 4 5 times and multiply those 4s together. So you're going to get a whole lot bigger number than 20 when you do 4 to the 5th this way. You can always say it as 4 to the 5th power. You can say it 4 to the power of 5. And feel free to use this symbol on your keyboard in order to denote an exponent. Many times students are like, how do I put an exponent in there? This symbol, you can use it on your keyboard. It's Shift and the number 6. And it will actually place this symbol here to indicate an exponent. So looking at, here's one type of way you could see this question asked. What does the expression 3 to the 4th mean? Now remember, I said a lot of people answer A, 3 times 4, but it means so much more than that. 3 to the 4th means to write the 3 4 times and then multiply. So it actually is B, okay? C would have been 4 to the 3rd, right? That would have meant to write the 4 3 times, but our expression was 3 to the 4th. Okay, another way you might see this learning objective ask is, what's another way to write 36 using exponents? Well, in this one, I might work a little backwards. For instance, look at A, 1 to the 36. Now remember, that means to write the 1 36 times. And by the way, I'm not going to write it 36 times, but I want you to get the idea and multiply it. Well, I don't care how many times you multiply 1 by itself, you're going to get 1. Let's see what B says. B says 6 to the 2nd. That means to write 6 2 times and multiply. Well, that's 36. Let's check the others. C means to write 2 6 times and multiply. Now on that one, you're not going to get 36, you're going to get 64. And the last one means to do 6, write the 6 6 times and multiply. That's going to be a very large number, okay? And that's why we get B here. We would write it as 6 to the 2nd, which would be 6 times 6. So again, different ways to see this learning objective being asked. So let's think about, what does a negative exponent do to the number? Well, a negative number actually moves the base to the denominator, or the bottom of a fraction. For instance, if we look at 3 to the negative 2, we know that 3 to the 2nd, 3 times 3, would be 9. But because the 2 is negative, the exponent's negative, we write it as 1/9. So it brings it to the bottom of a fraction and puts the 1 on the top. Let's try these. All right, 2 to the 4th. Let me get a different color here. 2 to the 4th. That means to write the 2 4 times. 1, 2, 3, 4, and multiply. Now you can do the multiplication part with your calculator. It's totally fine to do that. If you need a free online calculator, please use Desmos graphing calculator. It's 100% free, has some really cool features on it. And in fact, one of the examples that I do for the assignment for this week, I use the Desmos graphing calculator. But you can Google that, and it'll be the first one that comes up. And you get 16. Now let's do number 2. We'll do 4 to the 3rd. That means to write the 4 3 times and multiply. And that will give you 64. Again, you can put that in your calculator. Let's do 9 to the negative 2. Now, what I do on this is I come over to the side and I do 9 to the 2nd. That means 9 times 9, which I know is 81. But because that exponent was negative, I have to write it as 1 over 81. Put the 81 on the bottom of a fraction, put the 1 on the top. All right, finally, let's do number 4, 7 to the negative 1. I'm going to come over to the side and do 7 to the 1st, which just means to write the 7 one time. But because the 1 was negative, I've got to write it on the bottom of a fraction with the 1 on the top. There, okay? Take your time with exponents, okay? Don't get in a hurry. When you get in a hurry, that's when you tend to get them wrong. Okay, another way we might see this question, this objective being asked is which of these expressions would give you the answer 0.125? Okay, this is another one where you should go to your calculator. Remember, I know the calculator on your phone probably doesn't have an exponent on it. You can use the Desmos graphing calculator. Desmos graphing calculator. You can Google it, and you literally can type these in as is, and Desmos will give you the answer. Now, I'm going to go ahead and do them. 8 to the 1st means to write an 8. 8 to the negative 1 means to do 8 to the 1st, which is just an 8, but put it on the bottom of a fraction. 8 to the 0. Anything to the 0 power is 1. Again, if you type that in your calculator will tell you. And 8 to the 2nd means to write the 8s twice and multiply, and that will give you 64. So the only one that could be even close to 0.125 would be the one that is less than 1, right? Because 0.125 is less than 1, so that would have to be B, the 1/8. Okay, we'll continue this idea with properties of exponents. So when you are multiplying like bases with exponents, you can add the exponents. Now, let me show you how this plays out, okay? Look at x to the 4th. That means to write the x's 4 times and multiply, right? Okay, then x to the 6th, and I'm going to get a different color so it'll stand out a little bit. X to the 6th means to write the x's 6 times. And multiply them. And the last one means to write the x's 2 times and multiply them. Now, how many x's do I have? Well, I know it's going to equal x to some exponent, so let's count them. I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. How did I get that? Well, I could have easily have taken 4 plus 6 plus 2. Ta-da! The shortcut is I could add the exponents together. Now the same holds true when I am dividing, but let me show you how the dividing works, okay? So x to the 9th means to write the x's 9 times. And multiply them. And then x to the 3rd means to write the x's 3 times and multiply them. Now what happens for every x that's in the top, you have one that cancels in the bottom. For every x that happens in the top, you have one that cancels in the bottom. So how many x's do you have left? 1, 2, 3, 4, 5, 6. So you get x to the 6th. And what was the shortcut? Well, the shortcut was I could have done 9 minus 3. So use the shortcut if you want. I show the written out part because it makes the shortcut make sense, okay? And I have students who are like, okay, I'm gonna write it out because I can see it. And that's totally fine, okay? Now, when you raise a power to a power, that's when you can multiply your exponents. So take the shortcut here. 4 times 3 would give you x to the 12. B to the negative 3rd to the 2nd gives you b to the negative 6. You can multiply those. But remember, we have a negative exponent. So we have to write that as 1 over b to the positive 6. All right. So let's try. Okay. We've got x to the 4th times x to the 7th times x to the 9th. So remember the shortcut. You can add those. So do a quick little arithmetic. We get x to what power? $20. Exactly. Yes. Okay. Now I'm a creature of habit. So on number 2, I stack these guys because I like to see them. I like to think of that written out part. Whether I write it out or not, I can actually picture it. Okay. So let's do the numbers in front part first. So 16 divided by 4 is 4. Now think about your x's, right? If you had those x's written out, you would have 2 x's on the top cancel with 2 x's on the bottom. You're going to end up with 3 of those x's left on the bottom. Write it out if you need to, okay? Then think about your y's. With your y's, you have y to the 9th on the top. And y to the 6th on the bottom. So think about it, you got 6 of those y's are going to cancel out, and you're left with 3 of them on top. Again, write it out if you need to help you see it. Okay, now our last one here, power to a power, we multiply the exponents. So I've got a to the 2 times 5. I've got b to the negative 3 times 5. So a to the 2 times 5, that's a to the 10th, and b to the negative 15. And remember what we do with negative exponents, right? We put it on the bottom of a fraction. And then if you want to multiply those fractions, you can. Okay, practice makes progress with these. So the more you practice with our exponents, the better you're going to get at them. Don't stress over like, oh my goodness, there's so much today. Take your time, okay? It will get better. You will get better. Remember, we're on a journey to get better than we are today with our math skills on it, okay? Let's look at the next learning objective, and that's to identify the three components of an algebraic expression. So when you see an algebraic expression, you have three things. You have three things that can be going on. You have variables. Variables are the letters involved. So if we look at our example here, the variable would be x. It's the only letter that's being used. Can you have more than one variable? Yes. Then we have coefficients. Coefficients are the numbers in front of a variable. So again, looking at our example, the 3 would be the coefficient because it is in front of the variable. And then finally, we have constants, and constants are numbers that don't have variables. So if you look at our expression here, the 7 does not have a variable, therefore the 7 is the constant. This is just vocabulary, right? Much like those number systems we did at the beginning, we're putting a label on the idea, we're putting a name to it. And so let's take a look at a way that you might be asked this, okay? Using the expression 5x plus 7. So we're looking at 5x plus 7. We want to know what the coefficient would be. Okay, the coefficient, remember, that's the numbers in front of the variable. So the coefficient here would be 5. Exactly, Rocky. Okay, what would the variable be? The variables are the letters. So in this case, the variables would be x. Right, Kellen, good. Okay, what would the constant be? The constant is the number without a variable. That would have to be 7 here. Exactly. Okay. So again, maybe the questions ask us to identify which of these, what are the coefficients, what are the variables, what are the constants. Let's go one step further. A little bit harder expression this time. Oops, come back. Sorry. A little harder expression this time. 2x plus 6y minus 8. So number 1, what would the coefficients be? Coefficients are numbers in front of variables. What are the coefficients? And it's plural because there's 2 of them. That's right. 2 and 6. What would the variables be? That would be x and y. Again, we got 2 of them because we got 2 variables going on. All right. What would the constants be? That would be really close, Rocky. It's actually -8. -8 there. Okay, so we got to take that sign with it. Now, which of these is not a term in the expression? Okay, so 2x, well, I can see the 2x in this expression, so I know that's not it. 6, well, I see 6 in the expression, but the 6 isn't by itself. Okay, so 6y, I see that, that's in the expression. And I see the -8 in the expression. So it has to be B. Since the 6 is not by itself in the expression, then it's not a term. We have to have the entire term with it. Good work on that one. All right, our next learning objective is to look at equations that are used in other fields. So for instance, we have electricians use this voltage equals current times resistance, V equals IR, okay? Accountants will use assets minus liabilities equals equity. And then pharmacists use this formula to calculate a child's dosage based on weight and an adult's dosage. So So we see formulas happen all the time. How do we use them? Well, let's look at this example. This is an example from an electrician. So we're going to use, oh, so sorry. We're going to use the formula V equals IR. So we use this formula. And we're asked for what is V, the voltage, produced with a current of 2 amps, so that's I, with a resistance of 13 ohms, that's R. So we take our formula, V equals IR. In place of the I, we're going to put a 2. In place of the R, we're going to put a 13. And now, because these are written beside each other, they actually mean multiply. So we are going to multiply those together to get 26. This technique is called substitution. We are taking the numbers and substituting them into the equation to find the value of a third variable. Let's look at one more. Here's the accounting example. Using the formula assets minus liability equals equity. If your assets amount to 500,000, that's A, and your liabilities amount to 150,000, that's L, what would your E be? Okay, so we've got our formula. Again, we're using our substitution. In place of A, we're putting that 500,000. In place of L, we're putting that 150,000. And that gives me 350,000. Again, substitution, okay? Pretty simple if we can get the right values in for the right letters. So I think that's where I would put my focus, is making sure I can get those numbers in the right places in the variable. In for the right variables, I should say. Okay, our next learning objective is for PEMDAS. Now, if you've heard of PEMDAS before, you know it is the order of operations that we calculate expressions based on. And we get PEMDAS from parentheses, exponents, multiply and divide, add and subtract. So this is where we will follow this order so that we are consistent with our order of operations. Now, multiplication and division are written in the same step because we do them in order from left to right. Addition and subtraction, we do them in order from left to right as well. So let's look at an example. If I'm working this example, I would start with the parentheses, meaning I'm going to calculate the 4 plus the 7 minus 3, okay? 4 plus 7 gives me 11, 11 minus 3 gives me 8, so I'm going to replace the parentheses with an 8. Now, exponents, I get to skip that step because this problem does not have any exponents in it. So next I'm going to do the division. So 10 divided by 5, that's 2. So I get 8 plus 2, which is 10. So parentheses, then exponents, multiply or divide, and then add or subtract. Okay, let's look at one more. For this one, we do the inside grouping symbol. So we have brackets, but we also have parentheses. So we start with the parentheses. 6 divided by 3 is 2. So I replace that with a 2. Next, we do the brackets, and that's where I do 4 times 2. Well, 4 times 2 is 8. So I now have 3 plus 8, and that gives me 11. Okay? Following our order of operations helps us to be consistent so that we all arrive at the same answer. Okay, for time's sake, I'm going to skip these 2 examples, although if you want to take a screenshot or a picture, you definitely can work those on your own. All right, so let's look at these two questions. Using PEMDAS, what is the first thing you need to do in order to simplify an algebraic expression? What is the first thing you need to do? Think about PEMDAS. What's the first thing you need to do? It's the P, right? Parentheses. Good. All right, number two, what is the last thing you need to do in order to simplify an algebraic expression? In PEMDAS, what's the last thing? That's your add or subtract. Exactly. And remember, we do those in order from left to right. All right. I want to finish up today with just a couple of examples of the distributive property. The distributive property is used when you have a number in front of a parentheses, or when you have a term in front of a parentheses, and you distribute that term to both elements in the parentheses. And when I say distribute, you multiply. So 2 times x would give me 2x. 2 times 3 would give me 6. Let's do it with the second one. X times x would give me x to the second. X times 7 would give me 7x. When we distribute, we multiply. Now, when we have two parentheses being multiplied together, we can use the distributive property, but it tends to come out with the FOIL. Let me show you what I mean. On this example, we would take x and distribute to x. Notice this is the first term in the first parentheses times the first term in the second parentheses. So x times x would give me x to the second. Then we distribute x to 3. This would be the outside terms. So x times 3 gives me 3x. Next, let's do the inside. That would be -2 times x. And now I'm going to multiply -2 times 3. Now here's the beauty in this, and this is the one step you don't want to miss, is notice these two are what we call like terms. They have the same variable and the same exponent, so we can add them. 3x minus 2x would give me 1x. And then I would leave the others. Let's see that FOIL method one more time. We'll distribute the x. So x times x is x squared. X times 7 is 7x. Now let's distribute the 4. So 4 times x is 4x. And 4 times 7 is 28. Now again, the terms that you can add together, same variable, same exponent, they are in the middle. So we can get 7x plus 4x is 11x plus 28. So I hope this helps with this week's topics. I know we covered a lot. Okay, now you have to think about beginning of any math class, you're going to have to do a little bit of review, making sure we understand all the details and kind of bring everyone up to speed. Remember, this 45-minute session is comprehensive. It covers all of the learning objectives for this week. I'm going to do another session tomorrow. If you want to come back, I'm going to do different examples, but I'm going to cover the same concept. I'm still going to cover all of the learning objectives for this week. So that being said, I hope you guys, this gives you kind of a launching pad to get started this week. I'm here to help. Please reach out. I would love the opportunity to help in any way that I can. And thanks for coming. I hope you guys have a great week. Bye now.